At the end of the last video, I said that my canvas abstraction made things easier, but I wasn't sure if it's gonna stay. The problem with abstractions is they come at some cost. If a computer is fast enough, you might get away with it, but on a 386, there's not a lot of wiggle room. And I definitely noticed that my game felt slower, subjectively. I didn't have numbers to prove it. So the first thing I wanted to do this week was to get actual data to see how bad things really were. The problem, I hadn't just introduced the canvas. I'd also increased the size of the visible map and added vertical scrolling. So comparing week 3 and 4 would be like comparing apples and oranges. Sort of. I wrote a simple benchmark. Draw a fixed number of frames and divide by the time it took. So basically frames per second, right? Not sure if it's the best way to measure this metric, but it's something. I took the code from week 3, stripped it down, duplicated it, and changed the copy to use the canvas. The first rough version already confirmed what I suspected, but I wanted more data. So I also benchmarked different scrolling speeds, since moving more pixels means redrawing larger parts of the map. Once everything was ready, I hit run and waited. I rendered 1000 frames per case, 5 cases, 2 implementations, so after 10,000 frames the results appeared on the screen. And as you can see, the canvas implementation, called impl2 here, was significantly slower. So the next step was to find out why. I suspected it had to do with the way I got pointers to pixel locations. In the old implementation, I calculated the pointer directly in the loop. In the canvas version, it's a method call. Now, when we take a look at the position of method, it looks pretty much like the code in the loop, right? So why am I doing this exactly? It's my workaround for real mode memory limitations. The biggest block I can allocate is 64K, a little over 320 by 200 pixels. So I wrote a canvas implementation that splits higher resolutions across multiple memory blocks. But these blocks aren't guaranteed to be contiguous, which means I can't rely on a simple calculation. So I introduced the position of method to hide those details. Of course, calling a method is slower than an inline calculation, especially if you're doing it at least 200 times per frame. That made sense, but I had no proof. So I started replacing the position of calls with pointer calculations, but it didn't get much faster. I ran the first benchmark case after every change, but it stayed at roughly 21 frames per second. It looked like I was wrong about my theory. So I ran the benchmark again, this time also including the first implementation, and that's when things got weird. What? The first implementation was now just as slow as the second. I ran it again with a bigger sample size, but the result was pretty much the same. Then I benchmarked all cases with both implementations, and again, almost identical. The problem wasn't really that they were now equal. That actually made some sort of sense, because at this point they were doing basically the same. The real question was, why was the first implementation faster in the first couple of runs? And I can tell you right now, I still don't know. It doesn't make any sense. Since I was so frustrated about not having version control last week, I'd started making copies of the whole directory, so I was actually able to go back to the first benchmark and run it again. And it was also at 21 frames per second now. What the fuck? The interesting part? When comparing the videos of the very first run, you can see that the first implementation was in fact faster. I checked the footage to see if I'd made changes that slipped my mind, but nope. So eventually I gave up trying to make sense of it and moved on. So back to square one. I reverted all changes in the canvas implementation and ran the benchmarks again. As you can see, the canvas implementation is slower, but not by much. You could even argue both implementations are pretty slow. I've always suspected that Pascal's move procedure wasn't the fastest way to copy data around, but again, it was just a suspicion. I replaced it with an assembly version from the Swag archive written by Wesley Burns, shoutouts to Wesley, and ran the benchmarks again, and damn, that was definitely faster. And it also made the tiny differences between the two implementations more obvious, so maybe my position of theory wasn't completely off. Next step, eliminate that call entirely. I moved the positions array, which contains pointers to the start of every line up to the base class, and updated all implementations. Time for another benchmark, and this time the canvas version was on par. I'm still not sure what's going on with the 61 pixel case, but it was good enough to move on. So let's compare different versions of the actual game. Here's week 3. The frame rate obviously depends on how much is going on the screen, but I guess it's about 13 frames on average. This is week 4, and you can see that it's slower right away, dropping to 8 frames per second. Once we move away from the water animation, it picks up a bit, but not by that much. Here's week 3 using the fast move procedure, much faster, probably around 17 FPS in busy scenes. And here's the current version. Starting strong, dips a little here, but there's a lot of redrawing going on behind the scenes. But it feels snappy, and I'd say it's about as fast as week 3 with fast move. Which means the canvas abstraction doesn't get in the way, and that's exactly what I was hoping for. Now, I didn't think I'd spend the whole week running benchmarks, but that's what happened. I don't want to complain though, because in the end it was definitely worth it. I just hoped it wouldn't take so long. But hey, it is what it is, and hopefully next week will be a little more exciting. I'll see you then.